All right, so this is where we'll talk a little bit about PCA. So, oh, did I not unfold these? Okay, so here's a little line again. But PCA, so PCA stands for Principal Component Analysis. And so I like to kind of break these words apart, especially analysis parts. So it's like, okay, it's something we do, right? So not super interesting. But this principal component, and this is kind of fun, is that the principal component here is saying that there are components that are more important. There's our principal ones, and then there might be lower ranked ones. And that's what PCA really does. It allows us to say, okay, there are some ways to kind of make up this graph. The component is our new axis, essentially. So you can think of drawing a new axis on your data set, or you can think of like rotating like, this X and Y axis, or shifting the X and Y axis, and that's your new axes, making your new components. And then we rank in this principle, in the sense of the thing, what is the most important axis? Do we get more information in this, shifted X coordinate, or do we get more information from the shifted Y coordinate? Okay, and that's what the big thing for this PCA is going to be. Technically, I won't go into full like math and everything like this, as they're technically Eigen Vectors is what these components are. If you have done anything like in, like, let's say linear algebra, or in physics, Eigen Vectors are used very frequently to basically find this part. But basically that's what's going on here, along with matrix transformation. These YouTube videos are both, I think, from 3 Blue 1 Brown, that talk about linear transformations and Eigen Vectors. If you're kind of curious about like what's going on here, this actually does a really great job of explaining, like visually explaining what's going on without getting too far into like the math. It will show math and everything like that, which I think is an important aspect, but I think it's even better to like see like how are these things formed versus just like how do you computationally make them. Okay, so I highly recommend these guys. So overview about PCA again is one thing. What we'll do basically, the kind of the steps that's going forward, excuse me, is we'll find the coordinate, like the center along the data. So basically, where is it centered in there? And we'll say, okay, that's where 0 is. So you can imagine like, okay, we'll find like kind of like the center of this data. And then we'll actually draw a new coordinate system on here. So I kind of drew this from last time, or like on the last notebook, as I can imagine just drawing like a line here. And then like you can imagine like drawing a new axis like right here. And so the center is right here essentially. And so we'd have 0, and then we have negative and positive. And basically what we're going to do is essentially going to find the axes that basically contribute the most. So we basically are finding a principal axis. We're finding the center and origin of that data on that axis. So you can imagine like this is where the center of the data is right here. You can see the center is kind of right here. And then we're going to say, okay, how far are we kind of spread from each other? What's kind of cool about this though is that all principal axes are always orthogonal, meaning they're always 90 degrees from each other. So what's really cool about that, when we hear orthogonal or 90 degrees on the axis, you can think of it, they're independent from each other. Basically, if you move in this kind of direction, it doesn't tell you anything about this up and down motion. Note, however, if I had like axes that look like this, you see how they're kind of like diagonal like this. That means as I move up and down here, I'm actually kind of describing this information here. But if they are orthogonal, 90 degrees, basically me moving up and down this axis right here tells me nothing about where I am on the left and right axis, this horizontal axis. Does that make sense? So PCA, what's really nice is that they will always make essentially independent axes from each other. Those components are independent from each other. Okay. So going back to here. So some example concept here. This is where I like to think of like, how you kind of build this up from like, okay, the mathematics will tell you how these things are. I didn't mention Eigen Vectors. The Eigen part represents, I think it translates in German about proper or characteristic. So you can think of it, I like to think of it as like the true, like vector, like the true axis essentially. Like what is the best way to describe this data? The proper, the characteristic. And the characteristic again is like based on the data. Basically whatever you have on that data set is how you describe the new axis. So I think it's kind of a cool kind of thing that you can say like data actually has like an inherent like determined axis that makes sense for itself. Okay. But some examples. So you can kind of think of like how this works. Is that if you go back to our housing project, remember we had certain features and some of these are not exactly, but like say we had the square footage, the number of like bedrooms or number of rooms, right? And then we might have something, but this was in the data set, but like you can think of like school ranking and neighborhood safety. you can kind of think how these might relate to each other. For example, like the size, the number of rooms and the square footage, that's really describing some kind of like overall feature of like how big the home is, essentially. It's like there's some kind of like overall feature called like the size of the home, right? And you can kind of think like square footage and number of rooms and maybe some other features that could combine together to describe this like size component. That makes sense? And then you can also think like, you know, for example, I'm talking about this neighborhood component. It's like, well, you can imagine describing, you know, how good is the neighborhood, you know, quote unquote, good the neighborhood. Well, that depends on things like the school ranking, how safe the neighborhood is, you know, maybe how many break-ins or how many, you know, crimes are done in the area. This might combine together to how good that overall neighborhood is. You can even say things like, oh, is there a park nearby? What's the nearest park? You know, you can start putting a whole bunch of features that would describe this neighborhood. And essentially that's what PCA does, is trying to combine these other features into like an overall important feature. And this is where, if you remember back to Model 1's project, collinearity, you guys remember like dealing with correlation and stuff like that. And you know, I think I might have said this a few times too, is that like yes, we're gonna just, what did we do if there was multicollinear data or features? Overall suggestion was, I know it's been a while, but
we would remove like the one where it's correlated with like multiple ones.
Yeah, we would like remove one of the data points. What kind of stinks about that, and I might have mentioned this before, is that you can get rid of the multicollinearity. However, you're kind of losing some information, right? Like by the nature of dropping information, you're going to lose some of that extra stuff that could help. PCA basically will combine things together, say, okay, this is the actual feature, and it'll include that fuzziness and overall. And what's really nice about that is that our PCA, our principal components, we can actually rank them and say, what's the one that explains the most variance, essentially? What's the one that's going to describe the most spread of the data? If the data can spread from left and right, along this component, you know, most of the variations there, that's going to be the principal component. Basically, there's the most variation. We get the most bang for a buck by describing that one axis. Versus if you have a secondary component, that secondary component still gives information, but it's not really, it's not as important. Usually this is described with like ellipses surrounding the data. So if you imagine like we have, I'm going to scroll up here again to my little data set. If you imagine we have our data set like this, you can imagine drawing an ellipse around like this. And you can see like most of like the variation is going to be in this direction, right? Like that's where it really varies. Essentially, if you can explain it on this axis of the ellipse, you can say, oh, this is going to have a lot more information, essentially. Like I'm already going to know where most of the data is. And then in this axis here, I know I'm not the best drawer, but this axis on this ellipse, you can see like, well, it's barely, you know, like it's got some information, but it's not going to give us as much information as compared to this overall major axis. Does that make sense? Okay, and this is where you can probably see, like, you know, if you remember back from grade school with ellipse, with a circle, we just need a radius. For an ellipse, you need a major axis and a minor axis. Kind of the same idea here, is that this is the major one, the minor, right? So this is the first component. This would be like the second component. Okay. So let's see here. Just see what time it is. We've got some time. All right. So let's see here. So yeah. So what's kind of cool though is that we can actually make all of these components, components from the original data. Let me ask you guys kind of a quick question. How many components can we have at most when we do PCA? Let's say we have n number of features. How many components can we possibly have?
I thought that you could have n.
That's right. Yeah. Essentially, like if you have the same number of features, right? Like they might not be in the same like direction. They might be adjusted from the original features, but you can imagine if it's completely random data on the X, Y, Z, and whatever axes you have, you need each of those axes to describe it. So at most, you will have n number of features. However, sometimes it's kind of like, well, like we can generate that many components, but it's like, you know, technically we don't need that many components because most of the other components are like little fluctuations. Like it technically gives information, but like not a huge amount of variance between the two. So we can actually reduce that. And this is actually where it goes really well with dimensionality reduction. We can actually say, okay, instead of going from like, let's say 10 features, we'll get 10 components and they're all ranked. We can say, okay, let's pick the first like top 2 or 3. And basically that means that most of the information will hopefully be described in those first 3 components. And will we lose information? Yeah, we're going to lose some information by dropping the other ones, but we're going to lose as little information as possible if we keep the higher ones first. Does that make sense? Okay, and it's kind of like the same way that I can describe this curvy function with just a single line. It's like, is that single line perfect? No, but it still won't lose that much information. If I have a little like axis right here and I map them all over onto that one little line, we would lose a lot of information if we dropped that major axis, this very first component. Essentially, there would be a lot less information available to us. Okay. So that kind of gives us like a little bit of like how we can use these, how we can use PCA for us. So what's kind of cool about this algorithm overall, it's unsupervised, which means you don't need to tell it like how to draw the axes. It will determine what this axis is, essentially. Note that I kind of said like, oh, the square footage, number of rooms, create the size axis. It's probably not going to create an axis that is meaningful in a human kind of way, but it's going to be the thing that's most optimal for describing that data. Okay, it's also great for creating new features from old features. So this is really useful in the sense to actually use this in the sense like, well, let me go ahead and make a better feature. I kind of think of it like super features. And it gives us also a higher rank. So a higher rank basically means that we can say, what is the most important feature of these, like, these new features? What are the most important features and what are the least important features? So we can drop those other ones, and that kind of gets rid of that extra noise. Think like multicollinearity, we're dropping those features, but those features contain as little as information as possible. And then what's really cool about this is that it'll always be independent. So you'll never have correlation, like you won't, sorry, that's not exactly right. They're independent from each other, they're orthogonal. So essentially it means that if you adjust yourself on one feature, it shouldn't be affecting the other features. It's trying to maximize that amount of like independence from each other, if that makes sense. Okay. So really quickly, when to use it, when you want to access latent features, so you want new features, like basically it's like these features could be combined together. So think of like multicollinearity. If you have a lot of multicollinearity, you can use PCA essentially to like make these super features. So you can think of like they combine together to make this one feature versus like trying to drop one or figure out how we should determine this part. Also dimensionality reduction. So one thing we can visualize higher dimensions. Imagine if you have like 10 features, there's no way you can draw out a 10-dimensional figure, right? But what we can do is say, let's do PCA. Say, okay, let's go ahead and drop everything for the top 2 components or the top 3 components. And that can help us get a better picture of like what's going on in the data set. It also can reduce noise. So remember, because we have PCA is ranked, we can drop those last few ones because they're mostly just noise. And this actually kind of makes it a little cleaner for us to be able to figure out what this data set is doing, or sorry, yeah, what this data set is related to. And so overall, it tends to be really good for pre-processing, better for performance. Basically, it means there's less things that are kind of fighting for like dominance between the 2 features. Essentially, it's like, oh, here is the super feature. And essentially we can drop the lower features, essentially saying these aren't important, and we can optimize our machine learning algorithm. Okay. So that's kind of overall. I know I'm kind of over right now on time, but do you guys have any questions about PCA and everything? Cool. All right. And yeah, the curriculum kind of goes through a little bit of this. I think so I'm out of time right now. I think what next time is. I do have a little bit of example of like how we can do this. Maybe I'll save this for next time. We'll kind of show a little bit of like what that coding looks like. Okay. Cool. All right, so I'm gonna stop recording here.